Respected member of track chair and dear attendees, I am Poornachandratejasvi from Indian Institute of Technology, Gandhinagar, India, going to present false data injection attack detection with feed-forward neural network in electric vehicle aggregator bidding price. In this presentation, I am going to include background, problem setup, methodology, result and discussion, followed by conclusion and references. In transactive framework for EVs, EVA and DSO in presence of ICTs, we have a physical layer where we have the physical distribution system with EVs, electric vehicles and electric charging station along with a different load. Then we have cyber layer where we have electric vehicle aggregator and DSO. There is always an interaction of EV, CV and DSO in the transactive framework. Based on the price signal, EV provides scheduled charging. EV provides the price and demand as a quotation for EVA. EVA aggregate and provide the quotation for aggregated demand and bid price. Further, EVA communicate to DSO for final demand and price. The DSO provide the information of power and price to EVA. The price signal are communicated to EVA. So in this work, mostly the price signal from EV to EVA are communicated, and once this aggregator EV aggregator aggregates the price and power, these are sent to the DSO. Now the attacker or the we can say adversary may take an opportunity to manipulate the price and demand signal at EVA. To understand the detection framework, simplified FDI model is proposed. In this model, the actual price and demand are manipulated with some random manipulation of price and demand. The equation shows the simple addition and subtraction using the random number, where A denotes the attacked variable, lambda is for price, and P denotes the power, that is the aggregated power of EVA. Now, in following section, there are some nomenclature in which important are like EV relates to electric vehicle, EVA is the electric vehicle aggregator, FDI is the false data injection, T is a time period or a time slot, lambda denotes the price signal by EV and EVA owner, DA denotes the day ahead price, and cap denotes the maximum cap. Mu denotes the charging urgency, P is the EV charging power, SOC denotes the state of charge, D is the number of time step, delta T is the time duration, and neta denotes the charging efficiency, E is the battery capacity, PEVA is the aggregated power at EVA, and alpha or A denotes the attacked variable. The minimum and maximum, this superscript denotes the upper and lower bound. The detection framework is a data-driven model to generate the data in a transactive energy framework. Here the EVA user uses his optimization framework, and this framework consists of minimization of charging cost, and this charging cost depends upon the day ahead price, which is denoted by lambda, and P is the power for the duration of time delta T or a step time delta T. The charging power, which is subjected to the charging limit, that is minimum and maximum power. Then the target SOC at the time of arrival and at the time of departure, following by the SOC calculation, which includes the efficiency and battery capacity. Now, this framework, optimization framework, is run by the EV user to denote the price and the power during the charging slot with the aim to minimize the charging cost. Now, once this EV user solves the optimization problem, the information of each EV are sent to the EV aggregator, that is the aggregator. In this EV aggregator uses all the EV user price and power and codes the final price and power for a DSO. which is represented by equation 5, and this equation 5 denotes the expected value of quoted bid price for the volume of demand from the aggregated power. The detection framework at DSO level is simple feed-forward neural network. In feed-forward neural network, the input are the required power demand, that is PUVA, and the day-ahead price, that is lambda DA, are fed as input to the feed-forward neural network, and the output are the bid price, that is lambda EVA, that we call it as a predicted P. If the difference between the actual bid price and the predicted is less than tau, that is a threshold value, there is no manipulation. If the difference is higher than this threshold tau, then there is a manipulation in data. The proposed detection framework is implemented on 33-bus distribution system. This 33-bus distribution system consists of commercial node and residential node, which means that the commercial EVA, EV, and residential EV. The data preparation follows that there are total 10 number of EVs at each node. Hence, total 170 EVs at 70 different nodes are available. EVs are categorized as residential and commercial. The data for 24 hours is constructed considering the price signal. The day ahead price for 96 block, that is 15-minute block for 24 hours, is shown in this figure, and the time slot begins at 7 a.m. in the morning. EV charging power and bid price at node 7 is shown in this figure. The EV user runs the optimization to find out the bid price and power depending upon the day ahead price, and the EV aggregator aggregates the power and bid price at node 7, and this the information is shown in this figure. Error histogram during training and validation of feed-forward neural network is shown in this figure. This error denotes the difference between target and the output, and the error which is taken as a threshold is 0.1339, where we can see the measure of the instances, which are approximately 450 instances, where the data is divided into test, validation, and training. This is taken as the threshold. Now if you look at here, we consider the slot number 64 and the node number 3. This is the actual bid price, and the bid price is manipulated, generating some random number, and which is shown with the orange color. Now when the data of the day ahead price and the power demand is given, the predicted is something which is like 4.1 around. And if you look at the difference between the attacked price, which is the manipulated and predicted, the error is too large, and this indicates us there is a presence of a manipulation or a bad data here. Similarly, similar observation can be made for the other node number, where we have, let's take an example for slot number 68. This is the actual price, and this price is manipulated, which is said to be the attacked, and the predicted is something predicted price, and the difference which is very large. And in the same way, the manipulated data can be identified in the rest of the node considering the slot number. So this provides us a simple framework for the attack detection in electric vehicle. Now, electric vehicles are vulnerable to data injection attack in transactive energy management, and it is shown that EVs are prone to FDI attacks in day-ahead market, and attacker injects the FDI in the bid price and demand signal. Hence, it is necessary for the DSO to identify the falsified bid. The feed-forward network can effectively distinguish the FDI attack, and the model only requires the historical data. In the future, the potential vulnerability of targeted attack on EVA and the impact of FDI on DSO is the opportunity to investigate. Following are the references used in this work. Thank you for providing an opportunity to present the work in this conference. Thank you. Thank you a lot.